So hello, everyone. We are very, very happy today that Igor Kadota is joining us to talk about his very exciting work on WiFresh mainly. Igor received the bachelor's and master's degree in telecommunications and electronics engineering from the Technological Institute of Aeronautics in Brazil. I'm sorry, he received another SM degree, master's degree in communication networks by working with Eitan Modiano at the Massachusetts Institute of Technology in 2016, and the PhD degree from the Laboratory for Information and Decision Systems, LIDS, at MIT in 2020. He's currently a postdoctoral research scientist in the Department of Electrical Engineering at Columbia University, working with Gil Zussman. His research is on modeling, analysis, optimization, and implementation of emerging communication networks with the emphasis on wireless networks and time-sensitive traffic. Igor has received several awards, including the Best Paper Award at Infocom 2018, which is really a major feat. The MIT School of Engineering Graduate Student Extraordinary Teaching and Mentoring Award of 2020, and the 2019-20 Thomas G. Stuckham Jr. Fellowship. So today he will talk to us mainly about his work on supplying fresh information with wireless networks, and we can hear the rest from Igor himself.
Thank you very much, Arif. Thank you for the invitation and for the kind introduction. Can I share my screen? Can you see?
Yes, we do.
Okay. So, Arif, thank you very much for the invitation. Thank you for the kind introduction. My name is Igor Kadota. I'm a postdoctoral research scientist at Columbia University. And today I'm going to be talking about WiFresh, which is an unconventional architecture for wireless networks that supports time-sensitive information, applications that rely on sharing time-sensitive information. And I'm going to focus, as Elif was saying, more on the implementation side of things, more on the system side. But there's a lot of theoretical background that actually was in collaboration with Elif that is part of this work. I'm mentioning this briefly in a few slides, but if you want to discuss it further, we can. But I'm going to basically focus on implementation, and this is ongoing work. We're still working on this. I'm still collaborating with Eitan on things related to WiFresh. So if you have ideas or you want to discuss things, please feel free. Also, please feel free to interrupt me throughout the presentation to ask clarification. I really don't want to lose anybody during the presentation, so please feel free to interrupt me at any point. And I probably cannot monitor the chat, so if you just want to like unmute yourself and speak, it's also great. It's okay. The introduction is this, right? So the motivation is emerging applications such as those like automated warehouses, Internet of Things, smart city applications, autonomous vehicles. And in those kind of applications that rely on sharing time-sensitive information for monitoring and control, you have this big problem, which is if you have data congestion, for instance, imagine you have this smart city application that has too many nodes generating too much data, and this data generates congestion. This congestion can lead to outdated information at the destination, as we're going to see today. And this can lead to system failures and safety risks. For instance, imagine that this autonomous vehicle here is receiving data from an antenna and in this smart city application, but this information is somehow outdated by 10 seconds. Then this car here can be making the wrong choice, the wrong decision, right? And this can lead, of course, to some failures in terms of the smart city application, but also to safety risks for pedestrians crossing the road, right? So this is the kind of a problem that we want to address. And to address that, we propose WiFresh, which is an unconventional architecture that is built upon years of theoretical research, which includes a lot of work that we did with Elif. And WiFresh aims to achieve near optimal information freshness in wireless networks of any site, even when the network is overloaded. We're going to implement WiFresh in two different ways. So the first way is we implement WiFresh at USRPs at the MAC layer using the FPGAs of those USRPs. So this is one implementation of WiFresh. The second one is an alternative implementation that is much easier to implement, but the performance is a little bit worse. So the second one is an implementation at the application layer just using Python. So here we actually change the MAC layer of the communication or of the communication protocol. Here we are just adding some lines of Python code to the application layer, no change on the core of the network, but still we can get good performances in terms of information freshness, as we're going to see. And using this MAC layer implementation in the FPGAs, we can get 2 orders of magnitude improvement in terms of information freshness in the network. So this is what we're going to show. We have a video for this also towards the end of the presentation. So this is what we're going to be talking about today. And this is the outline of the talk. We're going to start by describing this large-scale monitoring system that uses Wi-Fi. And then we're going to go through theory rather fast, but basically here what we're going to do is we're going to introduce age of information, which is a metric that captures information freshness from the perspective of the destination. And then we're going to formulate the age of information minimization problem, and we're going to show how this relates to this large-scale monitoring system. And then we're going to formulate this problem of minimizing age of information, which is the same as optimizing information freshness. And we're going to show some theoretical results. In particular, we're going to show a lower bound on age of information, and we're going to show also the performance of some scheduling policies. But again, I'm not really proving any theorems here. I'm just stating some proofs and some of the results that we have. If you're interested, I can point you to the papers, or we can have a discussion about this. But this just to give you the correct context of background of this work. The real bulk of the presentation is going to be on system implementation. So we're going to describe, and then evaluate WiFresh in 2 different architectures, in 2 different platforms. The first one is a software-defined radio platform that we built at MIT. And the second one is a Raspberry Pi testbed with some dynamic nodes and some battery operated nodes. And we're going to talk more about this. So basically, we're going to implement and evaluate WiFresh on those 2, and we're going to verify that indeed our theoretical results can give us performance gains in terms of information freshness. So this is the outline. Let's start with our large-scale monitoring system. So consider this monitoring system with 4 mobile nodes moving with different velocities over time and generating position information, sending that position information to the access points, which then relays the information to the remote monitor. The remote monitor does not really know the current position of the cars. However, it has this last known position information, which is associated with the last packet it received, right? So it has this last known position information associated with car 4. And this last known position information is associated with a position uncertainty, right? Because the remote monitor does not really know where the car is. So there's some position uncertainty that we're going to describe further later in the talk. But now let's talk about the system from the perspective of the communication network. So here we have a car 4 generating packets of position information with a rate lambda 4 and placing those packets in the queue. And then car 4 fetches its header-line packets and transmit that packet to the access points. The access point receives the packet and relays this packet to the remote monitor. And as soon as this packet reaches the remote monitor, this last known position information here is going to be updated. And of course, that the position uncertainty is also going to be reduced because the destination just received new information about the position of this car, right? So the position uncertainty also reduces. There's a clear intuitive relationship between position uncertainty and information freshness, right? But now imagine that for some time, there's no new packet transmission, right? So no new packet transmission, so cars are moving, the position uncertainty is growing, but the last known position informations are not being updated. But now car 3 transmits a packet, then you have an update again, and the position uncertainty reduces. So this is how this system evolves over time. If you're familiar with age information, you can clearly see that this position uncertainty has a relationship with age information, right? But if not, you can see that the more outdated the information, the larger is the position uncertainty. So this is how the system evolves. And this system would work great if the system had 4 cars, right? However, if you have a large-scale system with 10, 20, or 50 cars in your system sharing the same access points, then we're going to run into a problem. Right, so imagine here that we have a communication protocol, let's say just Wi-Fi, but here really what I mean is that is any communication protocol that relies on first come first serve queues, which is the great majority of them, and also a communication protocol that uses random access. So first come first serve queue, just if you're unfamiliar with this, is just whenever a source generates a packet, this packet goes to the back of the line. Right, so the head of line packet is always going to be the oldest packet in your queue. That's the definition of a first come first serve queue. And random access is any protocol in which whenever a source has a packet to transmit, it wait for a random period of time and then transmits this packet. If by chance this is the only source to transmit a packet at this moment, then this transmission is successful. Otherwise, if by chance two or more sources choose to transmit at the same time in the future, then you have a packet collision. So packets are going to overlap, and then we're going to have a packet collision, and the access point won't be able to decode those packets, right? So this is basically going to be a waste of resources. Now, imagine that you have 30, 40, 50 cars in your system. Right now, as you're scaling this system, the probability of a packet collision is going to increase. So the waste of resources is going to increase. And you're going to have less transmission opportunities per source. So imagine that you have a system in which cars are generating position information with a given rate. However, they are having less opportunities to transmit those packets. So you're going to have more packets in your queue, which means that the packets they're going to, for each source, right, they're going to take more time to go from source to destination. So let's consider this from the perspective of the remote monitor of the destination, right? So I have a monitoring system which is scaling. I'm adding more cars to my system. And now the remote monitor is receiving less packets per car. And the packets that's receiving, it's also delayed, right? There's a high packet delay to receive those packets. So the remote monitor is going to have very outdated information about the position of those cars, right? And that's basically the main challenge they were trying to address, right? And you can clearly see how this can be an issue if you're talking about like a smart city type of application, right? A smart city application really needs accurate position information about the cars, for instance, right? But this goes beyond smart city and cars. This can be drones in a factory. This can be robots in a factory, right? In which you're keeping track of the position of the arm or something. When you really need accurate and time-sensitive information, you would like the information at the destination to be as fresh as possible. And this is when this kind of a problem becomes an issue. And if you look at the WiFresh paper, you're actually in the beginning, you're going to see a list of papers that use Wi-Fi. Because one question that I always get is like, if you're working with communication networks, the first thing they're going to think is like, yeah, okay, Wi-Fi is not built for this, right? But if you don't work with communication networks, people usually just use Wi-Fi. There's a list of papers that deployed systems in the wild, time-sensitive systems using Wi-Fi, and those systems work. If you have like 4 or 5 robots in your system, it's going to work. And I have a list there just to motivate why I'm comparing with Wi-Fi, right? And I was lucky enough actually to run into someone at a faculty at MIT, and he actually deployed one of those systems as part of the DARPA Subterranean Challenge. So they had those robots, they were deploying those robots in caves, and it was a team of robots, and they were communicating such that they could explore the cave more effectively. Right? The robots would split and then explore, and then they could come back and they would communicate, share information, and then go again and then split and explore the cave, right? And then this faculty was actually telling me that they had to scale down the system. They had like 7 robots, but when they were using 7 robots, the communication was very inefficient, and they had to scale it down because communication was an issue, right? And then this is one of the things that really motivated me and thinking that this is a big issue, right? That needs addressing. And to address this, we propose WiFresh, which has 2 important differences, right? The first one is less come first served queue, right? I changed the first come first served queue to a less come first served queue, in which whenever a source generates a packet, this packet skips all packets in the queue and goes straight to the head of the line. So this is the freshest packet in the queue, right? And this clearly should help in terms of information freshness. And another important change is to change from random access to scheduled transmissions. And I'm going to show you how this works. So the access point is going to run a scheduling policy, select one source, and send a polling packet to that source. Then that source is going to fetch its header line packet, which is the freshest one, by the way, and send that packet back to the access point. The access point will then relay this information to the remote monitor, but it will also update its belief about the network state. I'm going to be precise about what I mean here in a little bit later in the talk, but it's going to update its belief about the network state, and then it's going to run the scheduling policy again and select the next source to poll. And of course, here there's no collisions, and the data packets that are being sent, they're the freshest ones. So this clearly is an obvious choice for time-sensitive applications, right? And this is how we get the 2 orders of magnitude improvements in terms of information freshness. But we're not done, right? We actually added a new problem, which is how can we schedule sources, right? Which one of those 40 cars is the one that should send data packets right now, right? Given my current state of the network, the question is which car should the base station or the access point pull, right? And this is the problem that we're going to address next using kind of theory-based approach. Is the context and problem clear? If there are any questions. Awesome. Okay, we're going to introduce the concept of age of information. So here we have one source, the queue, in this case, a last come first served queue, and a destination. And I would like you to consider this timeline. And this timeline here, time throughout the talk is going to be divided into time slots. So here we have the blue arrows being the time slots in which packets are generated at a source. And the orange arrows, the time slots in which those packets are delivered to the destination. Right, so here is the number of slots between generation and delivery. So this is the packet delay of the first packet delay of the second packet, and this is the number of slots between two consecutive packet deliveries. So this is the inter-delivery time. So those are well-known networking concepts, right? I would like to use them to capture how old is the information from the perspective of the destination. And this is where information freshness really matters. So here I'm plotting age of information over time. And I would like you to consider this moment. This is the moment in which the destination just received the first packet, right? So imagine that I'm the destination, right? I just received this packet. Now the question is, how old is the information from my perspective? So I just received this packet. My information is going to be as old as the information contained in this packet. And the information contained in this packet was generated Z1 slots ago. So my information is going to be Z1 slots old at this moment. Right? My information is exactly this moment. My information is Z1 slots old. Now imagine that one slot goes by and I don't receive anything new. My information just became one slot older, right? And then 2 slots older, 3 slots older. So it's going to be like Z1, Z1 plus 1, Z1 plus 2, 3, 4, and so on. So it's going to increase linearly over time. And then until I receive a new data packet. Notice that here, there was a packet generation at the source, but I'm the destination. I don't even know that this packet was generated. This has no effect on me. But I received now a new packet, and now my information, my age information is going to be updated to the next packet delay, right? So Z2, and then it's going to grow again. So this is how age information evolves over time, right? So this is the sort of pattern that you always see in all age information papers. And I would like to emphasize here the physical meaning of age information, right? So if I say that at time t prime, the age information is 6 slots, this means that from the perspective of the destination, the information is 6 slots old. So there's a physical meaning to it, right? And if I'd like to keep the information at the destination as fresh as possible, this is the same as keeping this curve here as close as possible to 0. Right, so often in age information papers, you're gonna have an objective function, which is minimizing the area under this curve, right? Which means having a fresh data over time. And I really like this curve because it shows how hard it is to do this, right? So if you want to have low age of information to keep this curve low, to the area under this curve close to 0, you need actually 3 things. You need high throughput, because you need packets to be delivered all the time because you want the age information to go down. So you need high throughput. But you also need low packet delay, because when the age information decreases, you want it to decrease to something low. So you need also low delay. But you also need service regularity, because you don't want all packets to be delivered in the beginning and no packets at the end, because the age information would grow. So if I tell you that my policy optimizes for age information, it actually optimizes for throughput, delay, and service regularity at the same time. So this is how challenging this kind of a problem is. That's why there are so many research papers on this. Okay. So that's the concept behind age information. And if there are any questions, if not, I'll continue. Okay. So for simplicity in the talk, so this is not true in the paper, right? But in this talk, for simplicity, just to show the results in a more simple way, I'm going to consider sources that generate fresh packets at every given slot t. So, but the packet, this means that the packet delay is going to be always 1. So the age information, whenever there is a packet delivery, in the next slot, the age information goes to 1. Whenever there is not a packet delivery, then the age information increases by, right? So this is what I mean. Packets are generated at every slot, and we have a last come first served queue. So the packets always go to the head of the line. So whenever a packet is delivered to the destination, this packet was just generated, and the age information goes to 1. This is just a simplifying assumption because I want to show some theoretical results, and I don't want to go through all the nitty-gritty of estimating packet delay, right? So, but they are in the paper. Okay. So now we're going to formulate the 8 information minimization problem in a wireless network. So we're going to go back to our network, right? We just discussed 8 information. Now we're going to go back to our original problem of 8 information and position certainty. So here I have, again, multiple cars. And consider this piece of information here. This is the last known position associated with car 3, right? And I'm plotting here the 8 information associated with that piece of information here. And assume that at time t prime, the 8 information is given by 1, 2, 3, 4, 6. So 6 slots, right? At time t prime, the 8 information is 6 slots. This means that from the perspective of the remote monitor, right? This car has been moving around with velocity v3 for 6 slots without the remote monitor knowing about this. So that's why the position uncertainty, or the radius of this circle, is given by the velocity of this car times 6, or in general, the velocity of the car times 8 information, right? So there's a clear relationship between position certainty and 8 information. And if I would like to minimize the position certainty in this entire network, this is equivalent to minimizing some kind of weighted sum 8 of information, right? And that's exactly what's going to be our objective function, to minimize some expected sum of this 8 information here. Okay. So this is our network model. So I'm going to going back to our entire network. So I have n sources generating packets at every given slot t and placing those packets in less come first served queues. And each of those sources is going to have a different weights or a different priority, which is just a positive number. This can be, for instance, velocity, right? We have different weights and they're generating packets, placing those packets in the queues. And then the access point is going to, at every given slot, is going to schedule, it's going to select one of those sources. For instance, select source 1. Source 1 fetches its header-line packet, transmits that packet back to the access point, and then the access point receives this packet with probability P1. And then with probability 1 minus P1, there is a transmission error due to noise. So here I'm just characterizing the unreliability of the wireless link, right? And here we are allowing for different links to have different kind of reliabilities. So P is just a number between 0 and 1, which represents the quality of the link. P of 1 means that this link is reliable, transmissions will always get through. P equals to 0 means that this is highly unreliable and most transmissions would fail. And after the access point gets this packet, it relays it to the remote monitor. And of course, that the remote monitor is keeping track of the position of all cars, right? So it has one 8 information curve associated with each position, certain less known position of the cars, right? So this is associated with car 1, 2, and n. And basically the scheduling policy, so selecting the next car tuple should take into account all of this: the weights, the quality of the links, the current 8 information of the cars. And now I'm going to be more formal about what do I mean by optimizing, right? So this is our goal, to find the transmission scheduling policy by star that minimizes the expected weighted sum 8 information. And this is what I mean. So here we have the 8 information of car I at time t. I'm taking the expectation. The expectation here is taken with respect to the quality of the links, the randomness of the links, the randomness in the scheduling algorithm, also the randomness in packet arrivals, but in this case, I'm considering the packet arrivals are deterministic. So, but in general, this would also be an expectation with respect to the packet arrival process. And I'm multiplying this by a weight, and I'm summing over all sources, I'm summing over time, I'm taking the average, and that's basically my objective function. This is the performance metric that I'm trying to optimize, and I'm taking the limit as the time horizon goes to infinity, and I'm assuming that this limit exists. And now I would like to find a transmission scheduling policy by star that minimizes this quantity. And if I find this, then this is the scheduling policy that minimizes also position uncertainty in my network, right? And if W is velocity of the cars. So this is my goal. Now I'm going to go over some theoretical results. And here we have a picture of Aleph, which was a big part in deriving those theoretical results. So again, our goal is to find the transmission scheduling policy by star. The transmission scheduling policy by star selects in each slot t the optimal source to pull in order to minimize my objective function. And the first thing that I did, and this was actually my master's, was just throw dynamic programming at this and find the optimal policy. And this is by definition the optimal policy. The problem is that this is high complexity, right? So naturally, this kind of a solution would have an algorithmic complexity that grows exponentially with the number of nodes. right? And that's what we proved in my master thesis, right? This is high complexity, so we cannot really implement this on a Raspberry Pi or in an FPGA, right? So there's no hope of actually deploying this in a real system. So my next question was, can we come up with a policy that is intuitive, low complexity, and works great? And maybe some of you are already thinking about this policy, which is the greedy policy, which Ian calls this a maximum age first policy, which probably is a better word than just greedy. But we, in our paper, we call this the greedy policy, which basically at time t, it selects the source with highest age information. So at time t, I don't care about quality of the links, I don't care about priorities, I just care about age information. I look at the age information, I pick the highest one. So this is the worst one in my network, so I pick that one. And I send a polling packet to that source. And that source gives me a data packet back, and my age information is going to reduce. So basically, that's what the greedy policy is. Very low complexity, and we prove that this policy is optimal for symmetric networks in which all quality of the links are the same and all priorities are the same. And this is kind of intuitive results, not so easy to prove, but it's a rather intuitive result. You look at this and say, okay, this makes sense. If everything's symmetric, the only thing that matters is age information. So pick the one with worse, should be optimal, and it is. But the next question would be, can we be a little bit more broad? What if I give you a network which is not symmetric? Can we say something about those kind of more general scheduling policies? So next, we would like to come up with low complexity scheduling policies with performance guarantees, right? Because finding the optimal policy for general networks is something that is still an open problem. So, but what we did was we found policies which have provably good performance for general networks. But before we can prove those type of performance guarantees, we need to have a benchmark. And in our case, we derived this lower bound. And this is how this lower bound works, right? So you give me the characteristics. So I'm going to give you a lower bound. You have a network in your home, in your lab, right? And you have a network with these characteristics. So n nodes, and each node has a different priority, and each node has a different quality of the link. And you give me those quantities. And I'm going to just throw those quantities into this lower bound here, and I'm going to give you an age of information performance. And now I'm going to tell you that whatever it is that is your scheduling policy, it cannot have a performance which is better than the lower bound. You can come up whatever you want. It will never have a performance, an age information or information freshness that is better than this number here. So if I say that this is like 4 slots, then for this particular network, then there's no algorithm that can have a performance on age information that is better than 4 slots. So this is our lower bound. And now we're going to use this lower bound as benchmark to develop performance guarantees. So now we're going to discuss low complexity policies with performance guarantees. And now I'm going to tell you what I mean by performance guarantee. So I'm going to give you a policy pi. And I'm going to say that this policy pi is beta pi optimal. So pretend that beta is 2, right? This policy is 2 optimal. What does this mean? This means that whatever it is your network, so you have whatever network with n nodes, priorities, and quality of the links, the performance of my policy is never going to be worse than beta times the lower bound. It's never, in this case, it's never going to be worse than 2 times the lower bound. So the performance of my policy is always worse than the optimal, which is still an open problem. Nobody knows what this policy is. So my policy is always going to be worse than optimal, and the optimal is worse than the lower bound. However, what I'm telling you with the performance guarantee is that my policy is never going to be worse than beta times the lower bound, right? So this is kind of the performance of my policy is going to be sandwiched between the lower bound and beta times the lower bound for any network that you have. So this is the kind of performance guarantees that we are proving. And we are proving those for so this is again just restating my performance guarantee. And here I have the scheduling policies that we have, and this is basically a table summary of my entire PhD, right? So these are different scheduling policies that we developed, and those are the optimality ratios. So those are performance guarantees that we have. So here, for instance, we have a optimization rate randomized policy. We developed this using renewal theory, and we prove that this policy for whatever network you have is going to be 2 optimal. And this was actually a rather surprising result because this is a very constrained policy. This policy is stationary and is also randomized. This policy is actually unaware of the concept of age of information. It just selects sources randomly. And we can prove that if you tune this policy correctly, you can get 2 optimality, which was a rather surprising result. And if we simulate this policy, you can see that this bound is actually tight. We actually get a performance which is close to 2 times the lower bound. But now, then we also developed this policy, which is the age-based max-weight policy. Developed this using Lyapunov optimization, and we also proved that this policy is too optimal. But in this case, this policy, which is going to be the one that I'm going to implement in the real hardware, right? This is the policy that we chose. So this policy is provably too optimal, but when you simulate it, you can see that this is actually very close to the lower bound. It's very close to one lower bound here. So this is actually very close to the optimum for different scenarios, but we cannot just prove one optimality, right? We prove two optimality, so there's no way that the maximum was going to be worse than this. However, in reality, we believe that this is close to optimal in a variety of different network scenarios. And just for fun, we also did this Whittle index work. If you're interested in Whittle index policies, I'll be happy to talk to you about this. We showed that the aid information minimization problem can be posed as a restless multi-arm banded problem, and then we obtained the Whittle index policy in closed form, and we also obtained the performance guarantee. However, clearly the age-based max-weight policy is better. So that's why we chose this one. And I'm going to briefly talk about how this works. So age-based max-weight policy. The max-weight policy is chosen because it's intuitive, low complexity, and has provable performance guarantee. So it's too optimal, right? And this is how it works. At the beginning of every times.t, the access point is going to select the source I star with highest index, where the index is going to be given by this. So at the beginning of .t, the access point is going to compute this for all sources. It's going to have like a vector with all those indexes here for all sources with the different priorities, part of the links and aid informations. It's going to pick the highest one. It's going to poll that source. This policy is very simple, right? Very low complexity. And it's also very intuitive. So if you were to pick a source, even without Lyapunov optimization, you were to, because this index came out of Lyapunov optimization, we did not came up with this, right? However, if you were to pick some kind of an index, you would pick something like this, right? So you would like to pick a policy which has high priority, good quality of the links, and high aid of information. This is a policy that makes sense. And that's why we chose that one. So now we're going to go to the bulk of the talk, which is system implementation. Are there any questions or concerns? Anything that I can address?
Sorry,
Yes.
For the previous slide, did you try any order other than two? The next slide.
The next slide, this one? This?
Yeah. Yeah.
So that's a great question. This is something that we always get, like, why squared here? So this is not something that we came up with. This depends. So the workflow is like this, right? So you think about a Lyapunov function, and then you use this Lyapunov function in your Lyapunov optimization, and you get the index out of the math, right? The math is going to give you some index, and the math gave us this index here, so there's no like explanation. It just came out of the math. However, if you choose different Lyapunov functions, you're going to get different indexes. You can play around with Lyapunov functions such that you get, like, for instance, 1 here. But then we chose this because this is the one that you can prove true optimality. That's the one that you can prove this. If you use other indexes, you can get other types of proof. You can get 4 or 8 here, right? And in simulations, this is something that has better performance, right? So this is what I can tell you. But intuitively, what this actually means is that aid information has a higher priority, right? So if a node has a low quality of the links, it's going to have almost 0 here. It means that most of its transmission is going to fail, right? However, with time, if those transmissions fail, this aid information of this source is going to be high, right? But if you square this means that it's going to have a higher priority than than the weights or the quality of the link. So this is kind of what it means intuitively. And we tried, and which makes sense, and we tried different ones, but we can prove worse results, and they have worse results in terms of simulations too. So that's why we stick with this one. Does that address?
Yeah. Thank you.
Maybe I can have a question as an add-on to this one, Igor. So probably if you tried the absolute value of age or the fourth power of age, etc., you would be getting different throughput versus average AOI behavior. Did you try any such other powers than two?
That's a great point. We tried different powers, in particular one and two we tried. One was giving us worse result in terms of age of information, but we did not really look at the throughput part. But yeah.
Yeah, I said absolute value. Of course, in the case of age, you don't need the absolute value. But
Right.
yeah, so
I see your point. Yeah.
Age itself. So, but as you explained, this quadratic appears to give a high preference to low age. Clearly, it's not going to change throughput. We know that. I mean, what power you use here should not affect throughput as much. What do you think?
So that's an interesting thing, because when you change power here, you're going to change your scheduling policy, right? And then, for instance, you might be right. It might change. So imagine that you have a network with a bunch of nodes, like 3 nodes that have a good P, like close to 1, and one of the nodes has a low P. Usually, that low P1 is going to have a higher information because deliveries just don't get through, right? And if you have the squared here, the maximum point is going to have a higher preference for that one with low P, right? Because that's it. So you're going to have maybe a lower throughput because you're always polling that one and you're getting failed transmissions. And if you had a 1 here, maybe you give less preference to that particular node, but you have a higher throughput, maybe. That's one particular case in which you might have a change. But what I mean that in general, like if you look at the expected weighted sum age information in the plots for different, at least the different ones that I tried, which was 2 and 1, we get a clearly worse one, age of information for 1. Right? But yeah,
that's probably because of the delay performance changing with these different indices. Right. Anyway, maybe we could discuss that later on.
Yeah, definitely. But yeah, that's a question that we always get, like why 2, and have you tried other Lyapunov functions? And we tried several, but then there's always we were focused on theory, right? And we wanted to get like the best result in terms of like this optimal iteration, and this is the one that gave us the best one. For a while, we had a result which was 4 here, because we were using a not ideal Lyapunov function. But then in the latest paper, we corrected this to another one, and then this gave us 4, this 2, and this gives us this index, right? But yeah, that's a great question. Okay. Let's go back to the description now, more systems and more systems description. So here we have our network of radios. We have here the access point, and again, we have WiFresh, right? So we have less come first served queues in the sources, and have scheduled transmissions running with age-based max rate policy. So the access point is going to run the age-based max rate policy, which means just computing those indexes for all the sources and selecting the source with highest index. And then sends a poll packet, and the selected source is going to fetch its header line packet, which is the freshest one, and send this back to the access point. Then the access point is going to update its belief about the network states. And now, if you are used to work with systems, you can clearly see what I mean here, because those quantities, they are not known, right? So there's no oracle that's going to give me the quality of the links and the age of information. I have to actually estimate those quantities. So the access point gets the data and update its belief or its estimates of those of those metrics, and then it inputs those into the age-based max rate policy, which is actually like that, right? And then computes this vector, selects again the source with highest index, and then sends a polling back to that source, right? And then goes on. And I'm going to talk about how the estimate is done. I'm going to talk about it briefly, but I will address it. So that's how the WiFresh system works. And the main challenge for us was complexity of implementation, right? So basically what we are trying, our goal is to compare WiFresh with Wi-Fi, right? I would like to get a Wi-Fi system and then implement my WiFresh system and say, oh, I'm getting like 2 orders of magnitude improvement in terms of information freshness. And I can only get that if I play head-to-head with Wi-Fi, right? I cannot really implement something on a CPU or like in Python and I assume that's going to have the same performance as Wi-Fi. Wi-Fi is already optimized and they built it like in a very nice way such that it gets like microsecond timescale. And I had to compete head-to-head with Wi-Fi, right? So what we did was we bought those radios and we went into the FPGAs and we reprogrammed the MAC layer. So a lot of the timing, the estimation of things, it's run on the Mac, on the FPGAs, because we needed the microsecond timescale and we could not get that using CPUs. And this was months of work with a lot of undergrads and master students at MIT. But it was great, right? Because in the end it worked. But yeah, this was the main challenge for us. Another challenge was going from theory to practice, right? So when I'm proving theorems, this is nice, right? This is nice to work, but when you go to practice, then this is not given. You have to estimate clock offsets. This is not given. You have to somehow create an estimator that runs on FPGAs. So you have to take care of memory and such things. Another important thing that we ran into was packet fragmentation. We are always assuming that we have slots and packets fit into slots, and that's not always true. If you're sending images, that's not going to happen. So we have to deal with all of those things, which are interesting engineering problems, and we had to address them, and it was fun to do it. But that, nevertheless, a challenge. Another thing is barrier to adoption, right? I'm here in the beginning of the talk, I was saying that there are like a list of people that uses Wi-Fi for time-sensitive application, which makes sense, but it's not ideal. And I would like to talk to them and say, okay, I have this new protocol that can run in your system, and they're going to say, okay, how can I do it? And so you buy those radios, which are very expensive, and then you reprogram the FPGAs, and you're going to get 2 orders of magnitude improvement. Odds are that they're going to say that, yeah, I'm going to keep with Wi-Fi, which is good for me, and it's fine, right? So this barrier to adoption is something that we tried to address, and we were actually able to address, which is, so the question is this, right? We know what is the theoretical ideal system, right? What it should do with the polling and the less come first served queue and everything. The question that was posed to us was, can you have some lines of Python code that make Wi-Fi behave that way? So this is what we try to do. That's one thing that we were able to do, right? So you have like a NIC card with Wi-Fi, and on top of this, you just have your Linux operating system, and in that system, you create a program, a Python program, that interfaces any data generating software with the Wi-Fi system. So we have an interface there, and using this Python interface, I'm making Wi-Fi behave as if it were WiFresh. And we were able to do this with just some lines of Python code. And this is something that we are still doing. So in this WiFresh paper, we implemented this in Raspberry Pis and we put them on remote control cars. But actually what I'm doing right now with some folks at MIT is we have some drones, and we are making the Raspberry Pis control the trajectory of the drones in real time. And this is something that we're currently doing. It's not ready yet. We're still getting, working through the engineering, but hopefully it's going to work soon. So this is another challenge for us. And both of those things, both the USRP and the Raspberry Pi, they are in the paper, that's described in the paper. Today, I'm going to basically focus on this. I have 3 slides in the end about this. If we have time, I can go over it. And we can also discuss offline if you're interested. So let's go back to the USRPs. So this is how it works, right? So WiFresh is implemented at the MAC layer of those USRPs, and the remote monitor is just my PC lab there in Leeds, right? So, and the access point, in other words, this USRP is the one that coordinates the entire communication in the network, sending polling packets and estimating parameters and so on. So this is the complicated one. This one is simple, right? It's just generating packets and placing packets in the last come first served queue and waiting for a poll packet. This one has all the smarts. And basically, now I'm going to describe how we did this timestamp offset correction, and even why do we need this, right? So to compute ADO information, you basically want to see how fresh is information from the perspective of the destination, right? So here, imagine we have time of the access points, and we receive the packets from source 1, which has this timestamp tau1, And this timestamp is generated with the clock of source 1. So at the moment in which this packet is received, the information is going to be T from the access point minus this timestamp, which was generated in source 1. So there's an offset. If the clocks are offset, there's an offset there. And this offset might be different for different sources. So if this offset here is larger, maybe you're always giving an information which is wrong by like 2 seconds. I'm exaggerating, but 2 seconds for this source. So you're always picking that source instead of picking other ones, despite the fact that this information is actually fresh. So you have to create a mechanism that can correct for timestamp offset correction, can correct for timestamp offsets. And in the lab, we had a easier approach because all radios are connected using Ethernet. So I can just synchronize the clocks using Ethernet, and that works. For aid information computation, at least our experience is that you don't need microsecond offset correct. You need the offsets to be small, right? Because you don't want to give preference to one source as opposed to other. But if there's a small offset, that's fine. So we just use MTP from using Ethernet to correct all the clocks, to synchronize all the clocks, and then we can just run compute aid information. However, this was not true with the Raspberry Pis. With the Raspberry Pis, we actually implemented a protocol that would send time information back and forth to estimate this offset. Okay, so this is one problem. The second problem is learning the channel reliability. And the point is that we are not trying to improve the state of the art in estimating the channel reliability. We just did something simple that works. So we consider this time window of 0.5 seconds. And in this sliding time window, we get for each of the sources how many polling packets were sent and how many data packets were received. We compute this ratio, and that's our estimate, right? And then, as you're going to see, this is a good enough estimate for us. Okay, a little bit about implementation. So we implemented everything on this USRP 2974, which is composed of a CPU and an FPGA. In the CPU, we had only everything that was not time sensitive, and at the FPGA, everything that was time sensitive. In particular, we implemented all polling, max rate computations, so this is something interesting, right? Less come per served queue. Everybody, when I'm talking about time sensitive applications, they say, it's obvious that, less come per served queue should be the best one. Yeah, it's obvious. After the theory is done, it's very obvious. If you go to systems, there's no such less come per served queue. So I was looking, so for implementing things at Raspberry Pi, I went into Linux stack and I was looking for a less come per served queue there, a flag that you change and change to life, and there's no such flag. You can choose between a billion different fair queuing algorithms, but you cannot choose a less come per served queue. At least I don't know of any. So both in the Raspberry Pis and in the SRPs, we had to implement less come per served queue, which is easy if you're thinking about software stack. They use this a lot, LIFO queues in like software in Python. But when you go for communication, this is something very uncommon. You have to implement it yourself if you want to use something like this. And there are issues with this implementation. But okay, so we implemented this in FPGAs, timestamp processing, estimation, parameters, everything. And with valuable help from great undergrad and master students from MIT. So here are our test beds. We have 10 software-defined radios generating packets of 150 bytes. So I'm considering like machine-to-machine communication, small packets. And they're generating those packets with a frequency lambda. And I'm going to have like low lambda and very high lambda. And very high lambda is where I'm interested in. So like high traffic load communication. This is the access point. So we're going to measure the expected weighted summate information for the following systems: WiFresh, Wi-Fi, and that's the one that you have in your laptop. WiFresh, but here I consider WiFresh without the less come per served queue. A WiFresh with like a first come per served queue. And you're gonna see why I'm doing this. And I'm implemented Wi-Fi with less come per served queue, just to see how it would improve weighted information, right? And each experiment is gonna run for a total of 10 minutes, and I'm gonna get the expected weighted summate information out of this 10 minutes, and I'm gonna plot it. So these are the results. This is expected weighted summate information in milliseconds in log scale. This is packet generation rate. So this is like low load. This is very high load. And I'm interested in this position here because this is a network with large number of nodes generating lots of information. Right here, it's less interesting. You have like few packets, few nodes. All algorithms should do okay. Right? This is the place where I'm very interested in. And here you can see that standard Wi-Fi, the blue one, gives you an read information of 5 seconds. Think about a car moving at a velocity, a low velocity of 1 meter per second. This would give you a position certainty of 5 meters. This is not total aggregate position. This is position uncertainty per car. This is no way near acceptable. If you go with WiFresh, you have an read information of 10 milliseconds, which gives you 1 centimeter position certainty, which is almost 600 times improvements. This sounds like a cheat until you see at least a video. That's why I always make sure to show at least one video of this working in practice. So this is our test bed, 10 radios sending packets to this access point here. And now you're going to see this is my laptop, right? So my computer, here you see the area information. I'm not plotting the aggregate area information, plotting the actual area information of the 10 radios. So here is I'm overlaying the area information plots one on top of the other, right? Of the 10 radios. And here you have the number of polling packets sent to radio 1, 2, 3, 4, 5, and 10. Number of data packets received. Here's the window estimation of probability, the P. So P1, P2, P2, Pn, P10 in the case, right? So, and here you're going to see some interference max, right? So I'm sending polling packets, receiving data packets, but I'm also competing with Wi-Fi routers in my lab because I'm not running this in a chamber. I'm running this in the lab with competing laptops and people streaming videos and so on, right? So this was pre-COVID, so we didn't have so many videos, but still we had people working in the lab. This was middle afternoon, so we have competition for the wireless spectrum, but you can see that our system can also go back from interference and go back to, I didn't show you the performance. So if you look at the performance, this is like 20 milliseconds. So we have an average of something like 10 milliseconds, and this is where the 10 milliseconds comes from. And I'm going to show you a system with Wi-Fi. This is Wi-Fi, same system, same everything. I'm just switched the flag from WiFresh to Wi-Fi. This is 12 seconds, 8 information, 6 seconds, 4 seconds, and so on. So you can clearly see that there's like a huge difference between WiFresh, which was 10 milliseconds, and this, which is like orders of seconds. This is where the two are.
Igor,
yes.
Can I ask you something here? So,
yes.
So WiFresh in this demo is synchronized over Ethernet.
Yes.
Right, but Wi-Fi is not. Right?
They are there. We do synchronization. This is more of a habit. I do synchronization every time I start the test bed. I turn everything on and I synchronize and then I run. Okay. But Wi-Fi does not have any slots, or it doesn't really need anything. It's just
it's regular Wi-Fi.
Right. It only needs synchronization to compute the area information. Right. I think they're going there. Right.
Okay.
Igor, can I ask you a question as well?
Yes. Yes, please go ahead.
Sorry, I don't have the video and I'm in traffic. So in last come first serve, when the packet is received from one of the transmitters, you dump the rest of the queue, right? The older packets.
That's a great question. Yes. So in the US,
first come first serve, you probably keep those packets in the queue,
yes.
And perhaps that's the reason why you get an incredible improvement in terms of AOI. But what WiFresh does is, on top of that, by this max weight policy, you get another maybe 10 times improvement of AOI. Is that correct?
That's awesome. You already summarized my next 3 slides. Yes. So I'm going to show you where the improvement comes from, but you're exactly right. So in the US, okay, first I'm going to address the last come first serve queue comments, which is true. So in the USRPs, whenever you send a data packet, you drop everything else. You drop everything that is older. You just throw it away and you don't use it, right? In the USRPs. However, when you talk to systems researchers, you often get this comment, which is, what if I don't want to drop my data? What if I want the data to be sent if there is bandwidth later, even later, because maybe I needed to do some estimation of future. So imagine that I have the position of cars. Maybe I need the past data to do estimation of future movements, right? So what we did with the Raspberry Pi is that in the Raspberry Pi testbed, we keep all data. It's an actual less come first serve, just so that we have both, right? So you're right that the past data should be thrown out if you really care about performance, because you don't want to waste your bandwidth with older data. But in case you want to keep it for some reason, for some application layer reason, then you can waste your data and send it later if you want to. But it would not affect aid information to receive a node packet. Right? So that's the first comment. The first comment is regarding the impact of max weight and first come first served queue. So, and then that's my next slide. So here I have Wi-Fi, and here I have Wi-Fi with less come first served queue. So this is Wi-Fi, both are Wi-Fi, but I'm changing the queuing only. I'm changing less come first served queue from first come FCS to less come first served, and I get an 85 times improvement. And then I keep the queuing and I change from random access to max weight. And as Nora was saying, I get like almost a 10 times improvement. So, and this is kind of poor if I just showed you 85, it's 7 is not so great, but it's great, right? If I tell you I have an algorithm here that improves your throughput by 7 times, you take it, right? So 7 times is actually very good. So changing from random access to max, because a lot of people think, oh, with aid information, just change from FIFO to LIFO, you're done. Well, it's not really true, right? If you avoid the collisions which are given by random access, you can get another improvement of 7 times, which is not 0. Right, so here we compare those 4 exactly because we wanted to have this kind of a graph, right? See how much improvement we get from queuing, how much improvement we get from scheduling. Okay. So WiFresh, some things you note here, is the only one, WiFresh is the only one in which a higher packet generation rate always leads to fresher information at the destination. And this is something that I would argue that you want in your system. So imagine you have a time-sensitive application, you have a bunch of nodes, and then you're generating more data with your nodes. They're generating better data, more data. You would expect your system to behave better, right? And this is only true with WiFresh. With all other data, all other communication protocols, there's some point in which if you generate more data, it's going to be worse, right? So this is one point. And because of this, WiFresh does not need congestion control. You don't need, the more data you send, the better with WiFresh, right? So that's another benefit. I think, Elif, I'm a little bit behind on schedule, right? Because I can just do this too. And
well, no problem at all.
Yeah?
You don't need to skip a slide. It's up to you.
Okay. This is just about WiFresh app. So here, I ended the presentation in terms of USRPs. Now I'm just talking about the Raspberry Pi. It's just a brief description of what we did. So again, the question is, can you get something similar to this with Python without changing the MAC layer, without FPGAs? And imagine that you hate FPGAs, you don't want to program FPGAs, you just want, but you're great with Python. You want to do something to improve the information functions of your system. So what we're proposing is this, right? So alternative implementation in Python, we just downloaded the software to these Raspberry Pis, and we don't change anything in lower layers of the application or of the communication stack. So here, application, everything standard. We just add WiFresh app, and here the mobile node is a Raspberry Pi, and both of those live inside another Raspberry Pi. Right, so they are very light code. So here is some of our results. So imagine that you have those Raspberry Pis, they have GPS. So this is the GPS that generates data of 50 bytes in a rate of 1. This is just a rate of a GPS. And IMU, which generates packets of 20 bytes and with a rate of 100 packets per second. So here is where we get our traffic, right? So a lot of data being transmitted here. And here the camera is off just for this result. But in the paper, you have the result with the camera is off. And of course, that if the camera is on, this is even more pronounced, right? The benefit of WiFresh. And we're going to measure the expected weighted summative information. So here is the punchline of the paper. This is what I really wanted to show. If you have more nodes in your system, Wi-Fi is okay if you have, small scale system, 12 nodes, still okay. If you want to have 24 or more nodes in your system, and I didn't change anything here, I'm just adding more Raspberry Pis to my system, right? Because we bought like Raspberry Pi Zeros, they're cheap, we were able to buy a bunch of them. So you have an information here of 34 seconds, which is unacceptable, right, for a time-sensitive application. However, with WiFresh, you can see that this clearly increases linearly. So of course they're going to take a hit because you're adding more nodes to the network. So you're sharing the bandwidth with more nodes. So information fresh is going to degrade a little bit, but here is degrading sharply, right? There's like okay, and then horrible. With WiFresh app, the performance degradation is going to be linear, right? Which is the best that you can get. So this is kind of the result with WiFresh app, and of course that at some point we're still working on this, not this result, but we are integrating these into drones now, and we're working on this, and we're going to make the code also publicly available. But there's no big secret there. So yeah, that's the summary of the work. Please let me know if you have any questions. I'm sorry I was 2 minutes above time, but I'm happy to discuss offline too. If you have to go and want to discuss something offline, I'm happy to address questions too.
Thanks a lot, Igor. I'm sure there are some questions now.
Yeah, I have one more question, Igor, actually, and a comment actually about Edith's suggestion regarding throughput. The question is, the Wi-Fi that you're using here as a baseline is 2.4 gigahertz, right?
Yes.
So probably that sharp increase in the age after 12 is maybe because Wi-Fi has 11 channels, and as you add to 2.4. So have you ever tried going for higher, like 5 gig Wi-Fi? Maybe that increase would have been at 40, 45 nodes because we have more channels around 5 gigahertz. Is my question. Have you ever tried that?
Yeah, that's a great point. So we had the Raspberry Pi 0Ws, and so what you're saying is something that we consider, and we didn't change because the Ws, I think it was the Ws, that they couldn't go for 5 giga. They only did 2.4. So we had the issue that because we wanted to scale the system, so we couldn't buy all 3B plus or 4B Raspberry Pis, right? So we had to buy the cheaper ones, and those they could only run on 2.4. But you know, this is like to address the specific question. But if you think a little bit broader, what they're trying to do, it can always be the case that you can think about some physical layer improvement that can push away the problem, right? So you can always push from 24 to 40, but then I will argue, okay, if the Raspberry Pi has a camera, then have more traffic, and then this pushes the boundary, the sharp degradation closer, and then I can say, okay, what if we have a LiDAR, and then it pushes even closer? But I say, okay, then we use millimeter wave, and then it pushes a little bit away. But we never get rid of this point in which your system is going to be bad with Wi-Fi, right? Because we have like the first come first served queue and the random access. But with WiFresh,
so I think it has to do with the limitations of Wi-Fi, I guess, right? The number of channels is always going to be a bottleneck here.
So as an extension to that question, how far do you think the WiFresh app pushes that bottleneck point?
Right, so that's a great thing. With WiFresh app, there's no bottleneck point. It's always going to be linear. It increases, right? So if you look at this, it's always going to increase because you're adding more nodes, right? So you're adding 10 more nodes to your system. So now you have to poll more nodes. It's going to increase a little bit. However, because you have a less come first served queue, the freshest packet is always on top. And because you have polling, there's no collision.
Right. So the nodes will be implementing their own local last come first served queues.
Right.
Right. After a while, though, they will always be backlogged with the freshest packet. So in terms of throughput, maybe there's going to be a point at which the system is unstable, but in terms of age, it will always keep at least a low average age.
Right.
I'm sure you have some analysis in the paper. I'm so sorry for my ignorance.
No, what you're saying is exactly right. So the data information of, because if you think about the system, even with Wi-Fi, Oh, okay. Okay, I'm sorry. Maybe the problem is that I didn't explain how it works in terms of Wi-Fi. Okay, maybe that's the how it works like this. So I'm driving Wi-Fi to behave as WiFresh. So packets here. So here we have the GPS and IMU. They all stick to the application layer, right? So I'm getting data and I'm trying to send data to Wi-Fi. But what I'm doing here is that I'm stopping the data. So this WiFresh app, it keeps at the source, it keeps a LIFO queue that stores the GPS data in reverse order of, so it refreshes first, right? And it doesn't send anything to the Wi-Fi stack. It keeps it in the application layer. So because here is all FIFO, right? So I don't want any FIFO on my system. So I keep the data here, and the access point sends a polling packet. And then when the WiFresh app receives the polling packet at the application side, it releases one packet. So I'm making Wi-Fi behave as WiFresh. So there's no of course that if you think about bugs and there might be collisions and things like that, but if you're thinking about the ideal system, there should be no collisions. It should be a polling thing and with less comfort served queues at the sources. So you're making Wi-Fi behave as a polling system without changing the MAC layer. And that's why we claim that there's no, so we can add 2,000 nodes here. Of course, that you're gonna always degrade a little bit because you're having to poll 2,000 nodes. But that what we're saying is that's what you can get. You cannot get something that with a given, as you're saying, right, with a given number of channels and limited resources, that's the best you can get. So if you add more nodes, you're gonna linearly share those resources with the nodes, right? But what we claim is that we remove the bottleneck. We are not pushing it for here or there, whatever you want to transmit, however many nodes you want. So networks of any size with any congestion, that's the data information they're going to get. It's going to decrease linearly, degrade linearly over time, but that's the best type of degradation that you can get, right?
Mm-hmm.
That's kind of
okay. Thank you.
I have another question, if I may. In your hardware implementation, you use a single access point and a number of nodes, but in the introduction part of the presentation, you use the automated car example a lot,
right?
But the thing is that when it comes to 2.4 gigahertz Wi-Fi, the range is not that good, so you would expect the cars to continually change the access point all the time, and the access point uses estimations for the scheduling. So how would this affect the performance of the access point in terms of the estimations?
That's a great point. So okay, so you're posing a great question, and I'm gonna make it even worse for me. So if you think about Amazon, they have those automated warehouses, right? With those Roomba-like robots moving around, and if you read their papers, those Roomba-like robots, they communicate using Wi-Fi, just regular Wi-Fi. And if you look at those videos from Amazon, you can look on the ceiling. There are a bunch of access points. They have a lot of them. That's exactly so it's a very similar situation, right? And so I think that the main point of this paper is this, right? So I'm considering limited resources. So I have like one access point in this case, and this access point is gonna, if you don't do any kind of WiFresh thing, you just use regular Wi-Fi, you're gonna have this sharp degradation, right? So that's my main point. And if you do, you're gonna have graceful degradation of your system. However, if you wanna do one way of going, one possible alternative to going away with this threshold is to add more access points, right? So if my system does not work with 20 nodes, I add one more router and I split my into two, and then it works, right? Yes. Which is a fair point, but still my concern is that you never removed your constraint at some point. So we always invent new things, right? We always invent new communications, more traffic, more nodes, and you never removed your degradation point. It's still there. it's hidden behind some millimeter wave or more nodes or more something, but it's still there. So that's one thing. Another thing is you're talking about management. So one thing that I always argue is exactly what you're saying. So if you add more routers to your system like Amazon, you have the problem of management now. So ideally, you can even have like one router per Roomba. That's great. The performance is going to be awesome, but you're going to have problems of handover, right? And when that happens, you're going to have a delay into handover. And if you do it great, you're going to have at least a problem of, as you're saying, if you're using some kind of a WiFresh system, you have to pass over some kind of the parameters that were estimated before. Right? So I think that a great thing about WiFresh is that you can reduce the number of routers in your system, right? Because the system degrades in a nice way. So here, you don't have to buy 2 routers to become 10 again and have this performance, right? You can just like have 1 router and have this performance for you. So that's kind of the,
Yeah.
Did I address your question? It was a lot.
Yeah, actually most of it, but the only point that is missing in my mind is that when the nodes change access points so fast, when there are cars, they are changing the access points so fast, so the estimation is never done properly. It can never converge for the node because it changes all the time. It changes the access point all the time.
Right, you're talking about estimation, for instance, I think a key one that you're, so for instance, estimation of the age information, I think it could be done, right? Because if you know your offset with regards to one piece of hardware and you know it with another one, then you can always transfer your offset there and they would kind of already have something which is good enough.
Yes.
But in terms of quality of the links, you're absolutely right. That would be definitely an issue because you have a completely different channel. And I would even move it further, right? If you're using like millimeter wave and your car is moving, this estimation should be awesome, right? You should have a very good algorithm there to estimate your quality of the links because this is going to really affect you if your car is being blocked by something. So I get your concern that's a very valid one. I have no answer to that. What we needed to, so when we did the test with those cars moving, the communication was not bad. I think one thing that helps us is that people that work on physical layer and Mac layer, they have all those protocols to correct for errors, right? And try to keep the reliability as high as possible. So with Wi-Fi, what we see is that the reliability is always close to 0 or close to, it's always 0 or 1, right? So that's one thing that I can say about that, but I still get your concern that if you have a highly changing environment or you have nodes that are changing access points, then this kind of estimator is not good. I get it. Yeah, I think that's a valid point. One will have to implement some kind of a better estimation system.
Yes. Thank you.
I have a question and probably a combination of questions and comments. Is that okay? Okay, yeah, so
that'd be great.
I thank you for your great presentation. It was very nice to hear the whole story. And I think you have shown some substantial improvements in AOI or in weighted AOI using WiFresh. Part of that improvement comes from the fact that you are using last come first serve, which is almost free. Probably took some time for you to implement it, but principally, it's not a big deal to make that change. It shouldn't be. But the other one is a dramatic change because the Wi-Fi originally is a random access network. Okay, so you're changing with this polling messages, you're actually changing the random access MAC of Wi-Fi. Essentially, you make it a scheduled access network and implementing the max weight algorithm in a centralized fashion. Now here, there are several questions that might be raised. One of them is that, okay, is that a good thing? Is that a good thing to make it centralized? Because random access is something that we believe it has been around for so long. So why don't we really stick to the random access mechanism and try to do a distributed implementation of probably the max weight but still in a distributed way, without having to change the MAC layer as much as WiFresh did. So this is just a comment question. However, so this was the main thing that I thought, okay, so this is random. This should have continued to be random access. However, in WiFresh, we have changed the entire thing. And definitely this requires a dramatic change. Definitely, it took some time for you to implement it and so on.
Yeah, I think it's a great point. Yeah.
And second, this Wi-Fi, this is in this example, you're only carrying status update messages, and probably Wi-Fi is there not only for status updates. So it should be carrying other traffic, and status updates should be only a part of the overall traffic. Now, in this case, definitely the whole thing fails because the random access part still needs to evolve, needs to continue. So those are the things that came to my mind when I listened to your presentation. So I set the stage to you back. So
that's a great point. Yeah, yeah. So those are all points that we were concerned during the paper. So maybe I'm going to address the one about flexibility, right? So I think that's a great point. So Wi-Fi is not made for time-sensitive applications. For sending updates for autonomous cars should not run over a pedestrian. So it's made for multi-purpose, like Zoom meetings and emails and everything, right? So that's a great point. I don't think we should change Wi-Fi. Wi-Fi is great for that. What we're saying is that there are types of traffic, in particular time-sensitive traffic, that should run over something which is a little bit more controlled. And that's why we are proposing max rate scheduling. And the reason why we were proposing max rate scheduling is exactly this, right? So if you just change from Wi-Fi to from first come first served queue to last come first served queue, which is, as you're saying, is something that is not hard, you still need either congestion control, which could be done, right? Or you need, so what I'm saying is that because you have random access, when you scale this system, you're always going to have that point in which you have too many collisions, right? So your system performance is going to degrade because of that. And what we wanted to show here is that the only way that you can really get done, we don't need congestion control, and your system could scale degrading nicely, linearly, right? Is having both access, polling or not random access and less come first served queue. So you actually need both. If you just do one, you can get a nice improvement, but you're gonna still have the issue of too many collisions. Right? But we are only arguing that this is useful if you need it. Right? If you really need a system that performs for the particular purpose of that system, that I really need to have like millisecond rate of information, then we argue that you should go for something like a WiFresh, but definitely not for any purposes. And maybe to your point is that in Wi-Fi, as part of the Wi-Fi standard, there is the point coordination function, like PCF, which is basically polling. And it was never used. So it was there, it was in the standard, everybody could use it if they want, nobody chose to. I would argue that maybe we didn't use that because we didn't need this kind of a performance for systems using Wi-Fi. We were basically using Wi-Fi for emails and sending files and sharing music, not really for telesurgery or controlling autonomous cars. And for those kind of applications, I would argue that something more controlled without this kind of a severe degradation would be better.
But still, for example, for low packet generation rates, definitely, let's say there are 1,000 users, so you pull them one by one, and most of them do not have even packets, so those polling packets are wasted. But this only happens when the packet generation rates are low. Right. And I think there is a great merit. So I'm happy to see this, but I simply asked the question to raise those concerns.
That's a great question. And you're just saying something that is very important, and actually we had addressed that in the paper. So we have results in which you consider stochastic generation of packets with given like of course, theory papers, right? So we consider Bernoulli arrivals with rate lambda. And we addressed that in in the system. Here in the system, another part that I didn't mention, and that's why I assume that packets were generated at every given slot T. But one thing that we are also doing is we are, in this system, we are estimating the arrival process at the sources, and we're taking that into account because we didn't want exactly what you said. So we addressed that somehow in the paper. It's a great point.
Thank you.
Thank you.
We're coming at you with lots of difficult questions, Igor.
That's great. Yeah, it's fun.
Yeah, so people here are very interested in your work. So thank you for your patience. I mean, I'm sure we could ask many more questions. Well, maybe one thing that I could suggest on top of what Professor Akar was just saying is perhaps it's worthwhile trying two different user classes, part of whom are applying WiFresh and the other part being regular Wi-Fi users coexisting, and that could answer some of those questions. Status update type packet flows and regular packet flows.
Yeah, and
coexist.
in our latest InfoComm paper, we had we basically optimized Wi-Fi for no scheduling, only Wi-Fi with less come first served queue, and we computed what was the optimal contention window, and then we implemented the optimal contention window in the USRP testbed, and we run it, and we show that the theory matches the practice. That's maybe in that direction, right? So trying to optimize the information for a system that is distributed and runs random access with less come first served queue.
Very nice. Well, good, lots of good work.
Yeah, thank you for the many questions and very interesting questions. Very
it's
challenging
very
questions.
exciting. I mean, congratulations on actually putting all of this to practice.
No, you too. So we are the two ones that are working on this more, like implementing and then seeing that it works, right?
Seems like it. Yeah. You and our group, right?
But you're more efficient. You have more works going.
Yeah.
Yeah. I hope that more people would do this kind of thing. Right?
Well.
Yeah.
So any other questions from the audience? Well, I guess then we can let Igor go and enjoy the rest of what remains of his morning.
Yeah, good night. And thank you for the questions. Thank you for the invitation. It was a pleasure.
Thank you so much for visiting us today. Yeah. Hopefully, maybe you can visit us in person at some point.
Yeah, same here. Whenever if you're in New York or at MIT, let me know. I'd like to chat.
Okay. Bye, everyone.
Bye. Bye. Thank you.
Thank you.
Thank you for inviting me.
Thank you so much. Bye-bye. Thank you, Igor.
Bye.
Thank you. Thank you for the questions.